Does this look okay?
Yes.
All right, cool. Yeah. Let me know when I should start.
You can start now.
Okay. Hi, everybody. Welcome to CMU. It's exciting to see all the new faces. I wish we were all in the same place, but soon enough we will be. So yeah, I'm a faculty in the machine learning department. My broad interests are in democratizing machine learning, and hopefully that'll become more apparent in the talk I give. Right. So let's dive into it. So as I'm sure you guys all know, we are seemingly in this golden age of machine learning, and whether it's from a research perspective, we're seeing superhuman performance on previously challenging benchmarking tasks. We're seeing an incredible growth in just the size of the research community. From an industry point of view, we're seeing all the biggest companies in the world lean in really hard into machine learning and AI, and it's powering some of their kind of coolest advances. So, self-driving cars, voice assistants, translating applications, and so on. From an educational point of view, we're also obviously seeing this. CMU is a pioneer in being the first to offer an AI degree just a few years ago. At Stanford, I think at CMU, pretty much everywhere, computer science is emerging as the most popular major at universities around the world. Right, there's this natural, maybe the thought is that machine learning has already arrived and it is already being widely used. If not, it seems based on all this evidence that machine learning is certainly ready, at least for, in the near future, widespread adoption. So what I argue, and kind of what's motivating my research, is kind of the opposite viewpoint. I think we have a long way to go before machine learning is ready for widespread adoption. And as the title suggests, I think looking back, say 100 years ago to think about the field of aviation provides a good analogy of why we are where we are. So this is the picture of the Wright brothers, a picture of the Wright brothers in 1903. This is their seminal flight. They flew for tens of seconds and hundreds of meters, but this is a seminal moment in that it kind of moved powered flight out of the realm of science fiction and into the realm of reality. The Wright brothers and other folks kept pushing. This dawned the pioneer age of aviation, and just 7 years later, powered flight was demoed at the World's Fair, which was a really big deal, evidently, about 100 years ago. And at that point, powered flight was culturally accepted. The world people realized that it was going to change their lives fundamentally. But at the time, it was still restricted to just elites or if you were fighting a war, right? And in fact, it took another 4 decades before the commercial jet age commenced, right? So there's this question of what took so long, right? If the core technology existed in 1903, why did it take 50 years before we had planes that looked roughly like this, right? And what needed to happen was that aviation needed to basically be viewed as an engineering discipline. And it was democratized by advances in aeronautical engineering related to efficiency, automation, and safety. So more efficient turbine engines, automation in the way we create and test planes, and safety, again, in terms of new testing procedures and regulatory agencies to make sure it was safe for civilians to fly. And so bringing this back to machine learning, I would argue that we're in the pioneer age of machine learning. So the results of ImageNet in 2012 with deep learning kind of shattering previous benchmarking results was sort of like our Wright brothers or Kitty Hawk moment. It made us all pay attention, and it led to kind of what I talked about earlier in terms of lots of excitement and new energy in this pioneer age of trying to innovate in this field, right? And at this point, machine learning is culturally accepted, but it's still restricted to to some of the largest organizations in the world. And so the real question, what I call getting to the jet age of machine learning or kind of democratizing machine learning, it's not clear. Hopefully it won't take another 4 decades till we get there. But the point is that there's a lot of work left to do for us to get there. And I would argue that these 3 pillars, efficiency, automation, and safety, are a good beacon for the kinds of problems we need to be solving. So in terms of efficiency, we need to think about how to leverage massive data sets and massive hardware, as well as potential constraints in, say, edge or edge environments. So how do we do distributed training, efficient inference, things like federated learning where we're learning on remote devices, things like that. From an automation point of view, right, this subfield of auto ML has recently emerged. It's really been focused on these 3 tasks to a large extent: hyperparameter search, NAS, and meta learning. But it's this broader problem of how do you just automate the end-to-end machine learning workflow. And then finally, safety. right? I think this is emerging as thankfully, it's finally emerging as an increasingly important problem, and that the barriers to entry to using machine learning have reduced over the last decade, which means that more people are using machine learning, even if it's not fully democratized, more people are using it, which is kind of scary in its own right, because people who are using it without really understanding what they're doing can end up doing really bad things. And right, there's lots of horror stories about how machine learning has been used to introduce or reinforce existing biases or violate privacy and so on. Right, so this is kind of a broad umbrella of the types of problems that I'm interested in. What I want to talk about today is kind of two areas that my group has been looking at a bunch recently. So that's in the areas of neural architecture search and interpretability. So these talks are short, so I'm going to go fast and not get into nearly as much depth as I'd like, but I'm happy to chat more offline. Right, so in the context of neural architecture search, kind of the broader problem is this notion of training, tuning, and designing models, right? So here I'm focusing largely on deep learning models, and quoting here a paper from, I guess, 3 years ago now. It's a paper by a former colleague who's now a Google brain, or who was at Google Brain at the time, and they were training deep learning models for machine translation tasks. And the specific problem is not important as much as the fact that the models that they were looking at, each one took days to weeks of GPU time for training. And in order to tune the hyperparameters of these models required 250,000 GPU hours, right? So kind of doing some back of the envelope calculations, effectively they were training roughly 10,000 models to do hyperparameter tuning, requiring nearly 3 decades of compute time and $250,000 if you assume current cloud pricing. So that's really expensive and lots of models to train. So this hyperparameter search problem, which is a core reason that this was an expensive thing for them, is focused on this problem of you start with a fixed backbone, and I'm sure you guys are all familiar with this, but it's a good segue into how neural architecture search works. But you start with a fixed backbone for your architecture, and then there's some knobs you want to tune. Some are architectural, things like how many nodes you have per layer, the number of layers, maybe what activation function you're considering, but you're also looking at a lot of non-architectural hyperparameters. So things related to the optimization procedures you want to use, so the learning rate and the batch size and so on, as well as different knobs you can tune to hopefully improve generalization. So for instance, various notions of regularization of your objective function. So hyperparameter search, as we saw on large problems, is itself very, very expensive. But what happens if we want to be more ambitious and try to automate this procedure more? And so instead of assuming we have a fixed backbone that we know works well on the problem, what happens if we don't know that? And we want to start with just a broader search space where we actually want to learn the architecture itself. So effectively, what this means is, we're, instead of looking at kind of just coarse-grained architectural hyperparameters, we now want to look at more fine-grained hyperparameters as well. So things like, what actual operation are we performing at each layer? Is it a convolution? Is it a pooling operation? Is it something new, maybe that makes more sense in a new domain that we haven't yet discovered? And what does the actual network topology look like? How are nodes connected to each other? So something like ResNet, right? The skip connection was the key innovation there that made ResNets really powerful. Maybe there's other sort of network topologies that are really useful in new domains. And this is sort of what the problem of neural architecture search is aiming to solve. So how do I design a network kind of from scratch? And it's really focused only on architectural knobs, and it doesn't consider non-architectural ones. And kind of in theory, this is a really exciting application, right? We've seen a lot of activity from the research community about this, because this has the promise to replace what is currently a really ad hoc, expensive process that's restricted to experts, right? So expert researchers focusing on computer vision tasks like image recognition or specific NLP tasks, they're the ones today who are making all the innovations in sort of designing new neural networks. That doesn't scale to new applications that are not, say, of interest to Google or other big tech companies. And there just aren't that many experts in the world anyway to kind of spend years designing these architectures. So having a more automated way to do this is really promising. The problem is that the search space of architectures is really, really large. These are arbitrarily large graphs with arbitrary operations at each node, and the connections can be arbitrary as well. So the fully general search space, right? Modern neural networks. This is a network from 5 years ago now, GoogleNet. It's pretty complicated. Searching over spaces that include things like GoogleNet are basically intractably hard. So I'll get back to kind of this problem of the intractability of the search space a little bit later. But what people are currently doing today is solving this problem by looking at search spaces that are more constrained. They're less expressive, but they're more constrained such that search is potentially possible. So as I mentioned, there's been a lot of excitement about this field. I think starting in 2018 or so, at every major conference iteration, you'd see 10 or so new papers on neural architecture search coming out. Many of them, or pretty much all of them, were very empirically driven, trying to optimize performance on a few standard benchmarks. And so from our point of view, we kind of came into this as outsiders, making the observation that neural architecture search, while an interesting problem, is really a subset of this broader hyperparameter search problem. And so and we had been working on the hyperparameter search problem for a while. So my group came up with this method called hyperband, and more generally this notion of early stopping hyperparameter optimization methods that get really good empirical performance, are provably accurate, and are used widely in industry. And so kind of our starting point was asking this first question of how good really are NOS heuristics relative to appropriate benchmarking, relative to appropriate baselines, appropriate hyperparameter search baselines. And in fact, what we found was that while they're promising, hyperparameter search baselines like Hyperband are quite competitive. And this is kind of an important way to ground the field. For a field that's very empirically motivated and empirically driven, comparing against the appropriate baselines is fundamentally important. The next question, once we got interested and started digging more into this problem, we wanted to understand what algorithmic components really mattered. And again, this is going back to the fact that if there's 10 new papers every conference cycle on this problem, there's just a flurry of different algorithmic ideas that are out there. And my strong opinion is that simpler is always better, right? If I want something that I can eventually theoretically analyze and also deploy in practice, the simpler it is, the more likely I'll be successful in doing that. So understanding what actually matters and what doesn't is really important. So we ran extensive ablation studies. We found that certain components, which, beyond the scope of this talk, are particularly high impact. And based on the observations we found from answering these first two questions, we wanted to see if we could do better. Could we come up with simple, principled methods that also empirically worked well? And we've taken a first step very recently towards that. We've come up with a mirror descent-based framework called Gaia that we show provable convergence guarantees for. And actually, our guarantees are faster than for other methods. And it achieves state-of-the-art empirical performance on a wide range of leading vision benchmarks. Right, so that's kind of what we've been doing on NOS. Very briefly, what's next? This is going back to this question of the search spaces being too limited. This is, I think, the most interesting area moving forward. Fundamentally, what we care about in NOS, or at least what I care about in NOS, is empowering new people to use this technology, not to fine-tune existing, the existing latest and greatest architectures in computer vision or NLP. That's a fine problem to be solving. But that's, there's enough experts there who have the ability to make progress there. What I want to be able to do is kind of get the 90% solution in some new domain where you don't have access to an army of those experts. And the current search spaces right now are way too heavily reliant on expert domain knowledge on computer vision or NLP. If you make the search space too large, however, it's an impossible search problem. So kind of balancing these two concerns is something that my group is actively working on and I think is really promising and exciting moving forward. I'm almost out of time, but I'm going to talk briefly about work on interpretable ML, which is another area that I'm super excited about. And I think it is emerging more and more as an important topic. Like the safety problem is emerging as more and more of an important practical problem of machine learning, right? And so kind of a key point to make here is that there's not one problem here. There's a bunch of different applications, a bunch of different users for interpretable ML. It could be, how does a doctor convince a computational biologist to trust our predictions? It could be, how does an engineer explain their predictions to their bosses? It could be an ML researcher themselves trying to debug a model and improve performance, right? So the challenge here is that there's no single definition of interpretability among social scientists and certainly not among ML people. There's different goals for different settings, as we saw on the last slide. There's varying types of explanations, local explanations, global explanations, counterfactual explanations. And there's kind of no agreed upon way to perform evaluation in a way that the community can, standardize in a standardized way, make progress. So on one hand, this is a real problem. On the other hand, my group views this as a real opportunity. Right? We have the opportunity to define a new field. We can come up with new formal definitions and new formal ways and clean ways to do evaluation. We can come up with some of the foundational theory to connect these ideas with standard ideas from learning theory and understand and hopefully come up with new insights by doing that. We can devise new methods, and importantly, in order for this problem, in my mind, in order for us to make progress here, we really have to ground our work with real applications, with real practitioners who care about interpretability for solid reasons. And so, right, this is, all of these directions are ongoing work in my group, and I think it's a really exciting field moving forward. All right, so with that, I'll stop. Links to my papers and to a blog